So buffers are solutions whose pH don't change when small amounts of acids or bases are added to it. So its sole job is to maintain the pH, and it's going to consist of two compounds. Looking at these two images, to give you an idea, we have an unbuffered versus a buffer. When we add solution into our unbuffered, it's going to change color. So we used an indicator to see this change. That's not good. Typically for living systems, pH needs to reside within a pretty small or narrow window in order to stay healthy. So what a buffer does is you're going to add the same amount into a buffered solution and it's going to stay the same. That is the importance of buffers. Buffers are naturally within our body system. We have several different types of buffers. There's buffers in all aquatic ecosystems, anywhere where you have solutions that you can have acids and bases interacting. In order to maintain the living standards of those solutions, those buffers have to be there. Now the problem is, this is only small amounts of solution. It is possible for a system to be overwhelmed. If you just keep adding an acid, you just keep adding more and more and more and more and more, at some point the buffer is going to break and it's going to cause the system to break down and change as well. When that occurs, the buffer no longer works and you're going to see drastic changes to the health of the system we are looking at. We can have acidic buffers or basic buffers depending on the solution and where that pH of that solution needs to reside. Looking at acidic buffers first. Two compounds always have to make up a buffer because you need to have a compound that can react with additional acid and a compound that can react with additional base. Looking at the two components that make up acidic buffers. So first, compound 1. What makes an acidic buffer is the presence of that weak acid. So if we have our weak acid, like hydrofluoric acid, it will dissociate in water as hydrogen ions and fluorine ions. So we have our acid, and then we've got our conjugate acid and our conjugate base. If you go back to the strengths of acids and their conjugate bases chart that we have used before, we can learn to figure out where the reactants are being favored in this equilibrium reaction. Because F- is a stronger conjugate base, it's going to favor the HF. So that means in this solution, we are going to have an acid, HF, present that can react with a base. So now we need to have a conjugate base available within this system to accept reactions with acids. We know we need the conjugate base of the fluorine ion. So we take a salt that allows the fluorine ion to go into solution completely. And so we go back to the solubility rules. What metal can we put with fluorine to make sure it's always soluble? A group 1 alkali metal. So we can take sodium fluoride and put it into water. And when we put it into water, it separates the sodium ions, which are now spectator ions and we don't really care about, but they have no effect on the system. And we form completely all of the fluorine ions that was in that salt. That fluorine is that conjugate base. So now we have a conjugate base fully present with a lot of acid as well. So the concentration of your HF and your F- can react with the additional acid or base. But what happens when we add acid to this system, this buffered system? So if we add HCl, HCl being an acid is going to react with a base. So it's going to react with our conjugate base, which is the fluorine ion. The hydrogen is going to go to the fluorine ion and the chlorine is going to be in solution. So if you notice, when we have that acid, it reacts with the conjugate base, it reforms the weak acid that is part of this buffer system. Let's say we add a base. So if we have sodium hydroxide, that sodium hydroxide is going to react with our weak acid. So we're going to get sodium fluoride and water. That sodium fluoride is a salt. It is a soluble salt. It's the salt we used to free up those fluorine ions. So that's going to just dissociate again. It's not going to solidify out, therefore reforming more conjugate base. This process of reforming the two components that are required in this buffer system is what allows the buffer to work. So what you need is a weak acid, and you need the conjugate base of that weak acid, so the anion, in a soluble salt format. Basic buffers. So the major compound for our basic buffer is going to be the weak base. So our weak base here is going to be NH3. And when that dissociates into water, we can get NH4 plus and hydroxide ions. However, we are going to favor the weaker of the two, so our weak base is going to be present in higher concentrations than that of the conjugate acid. We need the salt of that conjugate acid, so we want to make sure that that NH4 plus is put with an anion that will make sure it's soluble. Because ammonium is always soluble, we can put it with anything, but let's just say we put it with chlorine. So we take that ammonium salt, put it in water, and it's going to dissociate into its ions. This allows us to have the conjugate acid to our weak base. So now we have a high concentration of our conjugate acid, we have a high concentration of our weak base. Now they can go and interact with additional acids or bases. So if we add some HCl, that acid is going to react with the weak base, NH3. It's going to form NH4 plus and chlorine ions. Well, there we go. We reformed the conjugate acid that is part of the system. If we react with a base, it's going to react with the conjugate acid. When it's going to react with that conjugate acid, we are going to get You don't need to know these reactions, but they're there for you. So the NH4 is going to donate to the hydroxide ion because it's in solution. So sodium's just there as a spectator ion to have the hydroxide, the base, present. So we're reacting with the base, which is the hydroxide ion. So that allows water to form, releasing that ammonia. Sodium was just a spectator ion to get hydroxide into solution. So with that ammonium ion, we reformed that weak base to continue to assist that buffer. So it's always just this going back and forth between an acid and its conjugate base or a base and its conjugate acid. But the important thing is it has to be a weak base or weak acid because we need to have it at equilibrium. So an example buffer system, our blood. So our blood needs to maintain a very narrow pH between 7.35 and 7.45. So we're going to have a buffer system in place. What occurs here is it really is regulated by the amount of CO2 within our system. And so that's what gets released into our blood and removed from our blood. When CO2 interacts with water, it actually creates a weak acid, carbonic acid. Weak acids can partially dissociate into their conjugate base and acid. So we can monitor the pH of our system by how much of this acid is present within our system. What happens is, because this is at equilibrium, we take Le Chatelier's principle in tow. We have our weak acid and we've got that conjugate base. So this is really our buffer system. But it's regulated by the amount of CO2 because CO2 is what starts this whole process. So if we increase the amount of CO2, based off of Chatelier's principle, so we increase the amount of CO2, it's going to force the equilibrium towards the product side. So it's going to make more weak acid, so it's going to have a more acidic process. If we decrease the amount of CO2, and so we're going to remove it, it's going to then roll back towards the reactant side, so the CO2 and water, away from that acid. So as we add more CO2, we become more acidic because we're making more H3O+. As we decrease the CO2, it becomes more basic because we see less H3O+ because that we're pushing it back towards the CO2 and water. Now we have to regulate this through our breathing, because when we exhale that CO2. We do inhale CO2 a little bit, but really where CO2 comes from is through our digestive process and cell respiration. So as we break down food, CO2 is a byproduct of that process. And so that CO2 then moves from our cells and into our bloodstream, up to our lungs to then pass through the alveoli, and we exhale it out. So we can maintain an even breath depending on our exertion. If you are just at resting heart rate, you're breathing very shallow. We don't have a lot in which we need to exchange. But as you increase your workout, you are making a lot, you're using cell respiration a lot more. You're going to increase the amount of CO2 in your system. So you're going to have to exhale that out in order to expel it so that your blood does not become acidic. So we have to closely monitor that pH. When you have that high blood pH, we have a decrease in the amount of CO2 present. So we're trying to reform CO2. That's called alkalosis, because alkyl is basic. So what it means is we are getting rid of CO2 faster than the blood can be supplied it from our cells. So that can happen from hyperventilation. So we're constantly exhaling and pushing out that CO2. If your cells are not readily putting more CO2 in the blood, you can create alkalosis. If you have a low pH, so that means you have too much CO2 in the system, you're going to get acidosis, acid. So this means we're not exhaling CO2 fast enough to push the equilibrium back. So this is going to occur during respiratory failure.